In the first part of this video we saw that our inability to measure time in the future suggests that space would have been stretched in such a way that time would have contracted to levels where we could no longer measure it. Even if the space remains still curved, time could not be assessed by the observer from certain limits of its contraction, then called subliminals. This would not be a problem in the universe, but in the memory of the observer, as it would depend on the direct measurability of time. A virtually two-dimensional space, with no measurable time, could not communicate anything to the observer directly. For this, the space would be dependent on a subliminal messenger, who could do it indirectly. Of the three variables available to take on this task, only the light remains. It would be present both inside the future cone of light and inside our cone of light from the past. Starting from the premise that space would have to remain constantly curved, even at subliminal levels, it ends up in the process of packaging light, known as quantization. Just as it would happen inside the future light cone, this process would not require time, justifying the impossibility of directly determining the curvature of the space. This is in line with the uncertainty principle, as we need to live the particles to allow them to be detected indirectly. In doing so, the light disturbs the particle in an unavoidable way. Furthermore, according to Eisbert, the uncertainty of the position or velocity of the particle would be a direct result of the quantization of light. As can be seen, the necessary timeless phase of quantization of light tells us that, even if the space curved at an earlier time, it would remain flat, at the level of its messenger. It is seen, in this case, that the quantization could be simulating or mimicking the curvature of space. It was assumed, in classical wave theory, that the quantization of all forms of energy would be related to time, which would not have been confirmed. For the point of view of those who observed the virtual flattening of the future light cone, due to the retention of light and time, it would have ended up in the space-time continuum in that post-Big Bang, and in the concept of continuous electromagnetic waves. Light and space would have become one. In addition, the virtual flattening of the cone suggests that the light would have been polarized in the process of its quantization, leveling its maximum and minimum energy levels. This polarization is the same that we see being projected instantly into our past, now unfolded in 3 dimensions. The late projection of information on the dome would give doubtful support to the Doppler effect, since the past no longer exists. The polarization of light allows us to understand why, from our point of view, everything in our observable universe seems to rotate in a circular and uniform motion. The future light cone obeys the geometric description of a straight cone, which has a perfect circle at its base. It would result from the turning of a right-angled triangle over one of its largest legs. After the apparent inversion in the direction of the arrow of time, already in full phase of space contraction, this cone of light, previously flattened, would unfold in 3 dimensions in our past, by adding time as an additional dimension of space. Here, time and depth of space would be confused, becoming the same thing. The curvature simulation, promoted by the quantization of light and the retention of time, becomes real in our past. Such a cone of light from the past would have its apex occupied by the observer. If, by virtue of the quantization of its messenger, the space presented itself as being flat, sooner or later the light, emitted in the Big Bang, would be everywhere in the universe. In the case of the solar system, you would not need to wait for 8 minutes to see the hypothetical death of the Sun, since the shortest distance to Earth would be a straight line. This description would be equivalent to that of a static universe that, because it violates the principle of uncertainty, would be placed beyond the reach of our memory. There would be no measurable time. Therefore, even if physically present in that stationary universe, the observer would have no way of remembering that. When astronomers use the Doppler effect to determine the position or speed of the stars, they start from the premise that the space would be flat, because what is taken into account in the Doppler is the necessary polarization of light. The infrared and ultraviolet would occupy separate positions at the ends of the light spectrum. The error of assessing the position or speed of a star when using its light tracking would be all the greater the actual distance in which it was placed. The difference of the future cone of light in relation to that of the past would be the depth of the last one. The first would have been reduced in its temporal dimension, while the other would have increased time in the form of depth, acting as if time were the third dimension of space. After spreading, the anterior polarization of the light would instantly project into the celestial dome. At this moment, it would no longer be possible to measure directly the time module in which the light would have been retained in our future. In the case of stars, information contained in the light they emit into space seems to reach us with immense delay, even though it is known that the future has not yet happened. We can see that, in addition to time, space would also be removed from the formation of the future cone of light of the event, because we cannot directly assess the changes in its geometry, as would be the case of its curvature. This would be done indirectly, through the space messenger. What we have left of the three initial variables, at least when it comes to our point of view, is light or cosmic radiation as a whole. That is, we are left with only the messenger, acting in isolation to indirectly define time and space. As the quantization of light does not demand measurable time, which is one of the mysteries of nature, it is confused with the very concept of a future light cone. When we describe space indirectly by light, we need to analyze the messenger's harmonic behavior, which is usually done by similarity with a mass spring set. It is possible to notice, in the experimental model, that there would be the involvement of conservative forces. The first phase of the simple harmonic movement of the light would be equivalent to the stretching of the spring. The second, that of its contraction. Let us, then, observe the connection between the cone of light of the future and that of the past. Our present moment would be inserted in the apex of X, which joins the two cones. The time spent in the future cone of light would be imaginary, as the future has not yet happened. For this time to take us to the subatomic level, and, therefore, to the apex that joins the two cones of light, this time would have to contract gradually, until reaching levels where we could no longer measure it directly. Thus, the spring of space, when described by light, would have its first phase taking place in our future, or inside the cone. This would be expected because, according to the theory of relativity, if space stretched in the future, time would contract in a complementary way. Thus, the inflationary phase should act, in its own time, as an immense information eraser. This would occur from certain limits of time contraction, still far from absolute zero. This is what happens at the subatomic level of matter. Without measurable time, movement could not be measured in the microscopic world. Newton's laws would not be applicable under these conditions of timelessness. Therefore, if the space stretched beyond certain limits, the light could not assume measurable movement inside the future light cone at the events. The movement of light and its waves, which is observed in our past, is irreversibly linked to time. That is, the expansion of time, or the contraction of space, is what allows us to observe the relative movement of light, which would have been incubated in our future. Then, the speed of light and the Doppler effect would be part of the same package, opened outside its own time. As everything indicates, it is the light that gives us the dimensions of space and the duration of time. For example, we conclude that the space is curved because the light curves itself. We do not have, at our disposal, another tool available, in addition to the cosmic background radiation, to measure changes in the geometry of space. The same would happen with time.